Okay, 9.3 is testing proportions. Now, again, whenever you see proportions, that's really just code for probability. So we're testing some population probability. Um, some test assumptions that you need to remember from before. R is a binomial variable. N is a number of independent trials. P is the probability of success and failure. We need to know that NP is bigger than 5 and NQ is bigger than 5 to take this binomial probability idea that these rectangles are going to fit underneath the curve. Your test proportions are either left tail, right tail, or two tailed. Your proportion is equal to some k, which is basically some number or a probability that you've accepted. If p is less than that number, then you've got a null hypothesis that's less than the accepted probability. You got a left tail. If it's greater than it's right tail, and if it's different, then it's going to be your two tailed. Now, some things to remember from the past. Your p hat is r over n. It's approximately normal. That means your mean is going to be your population probability. Your sigma is going to be p times 1 minus p, or you can think of it, if you remember this, q divided by n, and then take the square root. Make sure you divide all that out and multiply it before you take the square root at the very end. Okay, so those are some things to remember about what we did with proportions in the past. Now your z-score, and again, we're using z-score because this standard deviation that we're using is for population standard deviation. We're fitting it underneath the normal curve, not the student's t. Your p-hat again, NP and Q, you're going to take your z-score and you're going to find a p-value just like you did in the past. So state your null hypothesis, alternative hypothesis, level of significance. Just check to see that NP is bigger than 5, NQ is bigger than 5. Find a test stat, which is going to be a z-score. Use the standard table to figure out your area underneath the curve, so your p-value. Make your comparison for p-value to decide if you're going to reject your null hypothesis, accept a null hypothesis, and then make some sort of context-specific conclusion. So write the sentence about what you found. Okay, so it says San Francisco Chronicle reported that all students who graduated from the 8 campuses of the University of California, 30% of them finished their degree within 4 years. The remaining 70% took longer than 4 years to graduate. Suppose that a study was made of a random sample of graduates from Berkeley, part of the U.S. It's the one University of Cal system, where it was found that out of 385 graduates questioned, 124 had graduated within 4 years. Test the claim at a 5% level of significance that 30% of the graduates do so within 4 years. So can we use a z-score to test p? Well, here's how we're going to know. N, which is the 385, okay, times your 0.3 has to be bigger than 5. Oh, easily going to make it bigger than 5. 385 times 0.7 bigger than 5. That's easily going to make it bigger than 5 as well. So yeah, we can go ahead and do that hypothesis test. Now, we're going to test the fact that they say that p is equal to 0.3. Make sure you're using p, not mean. What do they want us to test it? It's, well, here. Doesn't quite say if it's less than or greater than. So what I'm going to make and use as my deciding factor is my p hat, my 124 over those 385. Where did I get the 124? Because 124 said they graduated 4 years out of that 385. Okay, just an inkling. 85. That's going to be 0.32. So maybe that might lead me to believe that maybe they're not right, that maybe that p is bigger than 0.3. So if that's bigger than, that's just going to help me know that it is going to be a right tail probability. So when I find my z-score underneath the curve, remember, I'm going to find that area right there. So let's go ahead with our z-score of 0.32 minus, so that's p hat, minus p, all over the square root of p, q, and n is the 385 that responded to our survey. So 0.3 times 0.7. I like to do the numerators and denominator separately. So on the top, I'm going to have 0.02 divided by our 0.8, there we go, and I end up with a z-score of 0.86. So I look up in the z-score table, don't have to worry about any degrees of freedom or anything like that, 0.86, and that gives me 8051. So this area right there is 8051. So the area I actually need for my p-value is the right tail portion, so it's going to be 1 minus that. So 1 minus the 0.8051. That p-value is 0.1949. Now, I test that to, what, 5%, so 0.05. There's my sigma. My p-value is 0.1949. That's going to beat it, so I am going to, at a 5% level of significance, reject, I'm sorry, not reject, fail to reject the null hypothesis that they graduate within 4 years at a 30% rate. They actually do graduate within 4 years at a 30% rate, according to the sample data that I got. Okay, so again, it's the same thing is really 9.1. It's just that you're using P as your testing, or not your test statistic, you're testing P, and you're using a P hat. So your standard deviation formula changed a little bit, but remember we're using a z-score. So again, here we go, page 522, 1, 3, 11, and 15 are all odds. Try number 6 as well. Do some of those before you get to class, and hopefully I can help you through some of those.